I need to whisper. Anyway, welcome this morning. The topic this morning, Introduction to Active Noise Control. I would point out that this lecture in particular was prepared by Yongfan Liu, one of my students who came to us from Eastern China Technical University, where he did his undergrad degree and then master's and PhD with us. The PhD, which he finished in, I guess, in the fall. And since then, he's been working on an active noise control project, which through some funding that he arranged in China with an electric vehicle company. So enterprising young man who's keeping us in touch with the modern world. I mention all of this because I am essentially a passive noise control person, right? Rather than active. So I am not the best person to give this talk, but we'll see. We can perhaps work our way through it together. So the active noise control really amounts to using secondary sources to generate sound fields in addition to the primary source, the source that exists in the space, with the intention of canceling the primary sound field either in a particular location or in the whole space, right? So people talk about local control, trying to control a sound field in a particular location, say around your head, or in the entire space, so local versus global. And normally this would result in, as indicated here, in a reduction of the sound pressure or power. For various reasons, the active noise control generally works best at lower frequencies. Perhaps the simplest way to understand that is that you need to, in the simplest implementation, you would need to put a secondary source very close to a primary source if you were to generate an out-of-phase signal that is intended to cancel this one. They need to be very close compared to a wavelength for that to be effective. And so, very generally speaking, things work best at lower frequencies. Also, there are timing issues involved, which means that delays, there are inevitably delays in the feedback and feed-forward procedures, which mean, and those delays are less significant at low frequencies than at high frequencies. So, very crudely speaking, a low-frequency procedure, and although this is the statement that always shows up in active noise control presentations. Passive control techniques are the way that Yongfan wrote this was that passive control techniques are not effective at these frequencies. As a passive noise control person, I object to that, right? Because you can often come up with specific treatments that in fact are effective at low frequencies, and we're working on things at the moment that are very thin, for example, and nonetheless are kind of effective. So, but anyway, you can take this for what it's worth. So I added the word sometimes here, sometimes not effective. And active noise control can adapt to changes in environment and noise sources, and that, in fact, is something that's kind of important and a powerful capability that active noise control systems can adjust themselves, and if conditions change, they can adapt to whatever is going on. So in particular, if temperature changes, or if there's a different number of people in the room, or da-da-da-da-da-da. So it is undoubtedly kind of flexible. And in the, again, just from a sort of general introductory point of view, this afternoon in the future trends section, I would say, I'll say something about active noise control. Active noise control is now sort of everywhere. in automotive applications. In the U.S., there are more than 20 vehicles that are being sold with active noise control systems embedded in them. Active noise control maybe got off the ground in the late 70s and then really blossomed, I guess, in the 1980s. The first demonstration of an active noise control system that I saw was in September 1977, so that's a certain number of years ago. At Essex University, where there was Barry Chaplin, who I think had the first patents on a sort of feed-forward control system for an automotive exhaust system. So he had a great little demo involving a little engine running away, and he could cancel the sound produced by that. So it sort of got off the ground with a vengeance in the 1980s, and then a huge amount of academic work which resulted in books like this, and then went sort of quiet for a long time because let's say, I think the signal processing technology got ahead of the hardware, but more recently we now have hardware systems that are robust enough to go into commercial products and be expected to survive for 10 or 15 years, I think. So the landscape has changed a bit, I would say, in the last 5 years or so. But these books, if you actually want to learn something about active noise control, are excellent sources of information. Phil Nelson, in particular, he was my office mate for 3 years when I was doing my PhD. He was the active guy, I was the passive guy, right? But his colleague, Steve Elliott, has written an excellent book on signal processing for active control, all of the stuff that you need to know from a signal processing point of view. Young Fan also likes this book by Sen Kuo from Penn State University. And I will also add that there's an active vibration control, or active control of vibration, I guess, book by Chris Fuller, Phil Nelson, and Steve Elliott that is also available. So in any event, if you can get your hands on these are excellent sources of information. The first patent, actually, which people sort of universally acknowledge, is this one by Paul Lug from 1936, which shows a sort of one-dimensional active control system in which a wave is propagating along this duct here. This is a microphone here, which samples the sound field, passes it along through this system to a loudspeaker that's flush mounted with the duct, and then projects a sound field that is out of phase with the primary signal, and so in principle would cancel the sound field. I'm not sure if there was any regard given to the influence of the secondary sound field on the microphone itself. We'll talk a little bit more about that as things go by. But as I say, so this was 1936, but really nothing happened. There was a little burst of activity in the 1950s, but then things really got off the ground in the 1980s. The next series of slides here are just really a whole bunch of applications, which gives me a chance to show pictures, right, without having to deal with equations. Something that I think you're aware has been kind of successful is our active noise control headphones that you often see people wearing on aircraft, for example. Also, the first sort of modern implementation of noise reduction in ducts was done by Larry Erickson when he was working for Nelson Acoustics, I guess, who were a muffler company in Wisconsin. And a kind of simple scheme, again, is sort of following the Lug patent, but in this case taking account of the feedback from the speaker, the loudspeaker, which is generating the secondary signal, back to the transducer that is sensing the primary sound field. So once again, just to be clear, the general scheme here is to measure some aspect of the sound field as it comes along the duct. You process that signal in some way, feed it to a loudspeaker, which then generates a signal that is meant to be out of phase with the primary signal as it continues along the duct, and so cancels the sound field in the duct. The error sensor here confirming the cancellation, or at least being used to help change the model so that the pressure at this point is driven to zero. The a more sophisticated, actually, example of, let's say, local control right at the eardrum here, involves this motorcycle helmet, which I was not aware of until the young fan dragged this up. But it's sort of interesting because there are a lot of noise sources, right? So if you're steaming along at 100 kilometers an hour or 200 kilometers an hour on your bike, so there's aerodynamic noise generated by flow over the helmet. There's turbulence under the leading edge here, as well as general noise sources coming through the helmet. And so this system entails both feed forward and feedback control to deal with the various noise sources, and apparently is reasonably successful. Whether there's enough computing power in the helmet, I'm not sure, but we'll see. Something else which a lot of people, well, a fair number of people are pursuing at the moment, is again let's say, local control strategy, where in an automotive application, instead of trying to reduce the noise throughout the entire vehicle interior, you just try to control the sound level in the vicinity of the driver's head, which is kind of convenient because there's an opportunity to put secondary loudspeakers in the headrest, for example. And then the issue really becomes one of where you are sensing, because it would be nice if you could put error sensors in the driver's ears, but the driver may object to that. So the error sensors are not placed very close to the head, and as a result, sometimes the performance is a little bit variable, and also things change as the head location changes, because the transfer functions between the loudspeakers and the points that you're trying to cancel also change. Just a note here that, which we'll repeat later on, but this is the spectrum associated with this particular application, and you'll see it's dominated by tones, big, strong, harmonic tones. And so this kind of signal is relatively easy to cancel because you can sense the rotation speed. Presumably this has to do with, say, gear noise or something to do with an electric motor. And so it's very easy to generate a signal, a stable signal that is in phase with this, and then invert it to create an out-of-phase signal, which can be used to cancel the thing. So Professor Mohanty was working on active noise control of road noise, and that would be a global control issue 20 years ago or so. And you'll see that people are still doing this in 2015. The issues there, as what's illustrated here, are various microphone locations throughout the car, close in the rear, in the front, in the rear, close to the driver's head, rear headrest positions, with various control loudspeakers. One of the things that I would have to say has enabled active noise control in automotive applications is the advent of relatively sophisticated audio systems in cars, where it's now sort of routine to have as many as 12 loudspeakers just as part of a conventional stereo system in a car. So those loudspeakers can, of course, be used to transmit music or speech, but also now are being used as part of the active noise control system. The challenges with road noise is that there are many, many noise sources, right, that contribute to the sound field in a vehicle interior. Specifically, each the tire road interaction at each corner of the vehicle serves as a separate noise source that produces noise in the interior of the vehicle. At the same time, there's aerodynamic noise coming over the car. There's powertrain noise, and then perhaps gear noise of various kinds. There's accessories, so the HVAC system, for example. So lots of noise sources, and in principle, you have to be able to generate canceling signals that are coherent with the various signals. So if you've got 10 incoherent sources, it becomes a bit of a challenge to measure reference signals related to all of those and to get them processed in such a way that they interact properly in the interior to reduce the sound field. So this is still a big challenge to make this kind of thing work properly. From a historical point of view, the first, let's say, mainstream application of active noise control was in aircraft. There was NASA in the U.S. put a lot of money into active noise control of aircraft interior noise, focused primarily on turboprop aircraft, so small regional planes with propellers. This, again, is a kind of ideal target for active noise control because of the periodic nature of this noise being generated by the propellers. And also the fact that you're in let's say, a relatively high capital environment. The aircraft are a lot more expensive than cars and are also maintained regularly. So they were a good first application. This plane was a test vehicle. It was being used by NASA, involving relatively large numbers of sensors and loudspeakers to generate the sound fields. We don't have, unfortunately, a picture of this, but the one aircraft the one group that adopted active noise control in a production aircraft was the Swedish company Saab. Their aircraft, the Saab 340B, is generally delivered with an active noise control system that is focused on reducing the blade passage tone from the propellers. If you may never have an opportunity to fly on a 340B because twin-engine turboprops seem to be disappearing in favor of small regional jets. But if you ever are on a 340B, you can see little spots where the microphones are, and the loudspeakers are hidden behind the parcel shelves and things like that. So, but it's an interesting aircraft. The other thing, another application that has been tested, but I'm not sure has ever been implemented. This was something that was done at Herrick with Luc Mongeau, Hyung-Suk Guk, and Matt Franchek, involving a scale model vehicle here. That was placed in a wind tunnel, I have to say, so that there was flow going over the top of this, which is meant to represent the interior of a vehicle with a sunroof. And so there's, perhaps you've had this experience where there's vortex shedding over the sunroof that then locks into an acoustic mode in the vehicle interior and produces very strong pulsations in the passenger space, which can be quite uncomfortable. The most extreme example I have ever encountered actually was in the Volkswagen Beetle, which where the sunroof seemed to me to be unusable because of this kind of effect. But in any event, these guys came up with, let's say, an active flap here. So this was not a system in which you put canceling sound into the interior, but actually tried to control the mechanism that was generating the sound. So there's this active flap at the leading edge of the sunroof that is trying to cancel or control the vortex shedding across the top of the sunroof that gives rise to the boom to begin with. This first time I saw this picture, I wasn't quite sure what it was. Right, it sort of looks like something you could put a cake in. Right, but sorry, young fan. This is. But if you've ever had an MRI, you'll know that there are pretty strong impulsive noises generated in the process of generating the electromagnetic signals. And so that can be disturbing to patients who are undergoing one of these tests. And so, sorry. We're just trying to get one of the monitors going again here. And so this device from 2007 is meant to be able to cancel that noise at the subject's ears. I'm a little bit, I didn't have a chance to talk to Young Fan about this, but a little bit puzzled about this because I understand with MRIs generally you're not supposed to have metal anywhere near them. And so what the microphone consists of, I'm not quite sure. So that maybe it's in a plastic housing or something, but nonetheless, apparently this works. And speaking of medical devices, you'll know that in hospitals there's huge amounts of noise generated by all the various machines that are being used to keep people alive, which I guess is a good thing, but on the other hand, you can't sleep, right? But there's some concern with all of the mechanisms involved with incubators for premature children, for example. And so this was an attempt, excuse me, to reduce some of the noise exposure for small children in that kind of setting. And whether this is a medical issue or not, I'm not sure. It may, but it may save marriages if you could actually come up with an active noise control system for reducing snoring. That would be very powerful. Something other than strangling, right? That's active noise control of a sort, but maybe intrusive. Young Fan has this in because I think the original application they were thinking of was in fact a sort of active pillow, as it were, which would reduce sound radiation. So anyway, so there are a whole bunch of examples. As I say, it's active noise control is now really entering, let's say, a mainstream, I think, because of advances in electronics, both in capability and robustness, as well as people have figured out how to do transducers that are going to, like loudspeakers, that are going to last for a long time and be reasonably robust. And now, right, having shown a whole bunch of examples, just a few comments about sort of general classification of things. Very broadly speaking, there are two possibilities here that you may want to do active noise control in free space. That is, if you've got, so this is something that SpaceX is interested in, whether it's feasible or not, but they have to do static testing of their rockets somewhere in Texas that generates a lot of noise, of course. And so if you could come up with a system that would cancel the noise as it traveled away from the test site, that would be useful to minimize the exposure to the community around the testing facility. So that would be active noise control in free space or in large spaces. And on the other hand, we have active noise control in enclosures, in confined spaces like rooms or automotive interiors or aircraft interiors. And in each instance, we have a choice, let's say, between local control, where you're really just trying to control a sound field at a particular location, or global control, where you are trying to control a sound field in the whole region, right? So everywhere. And there are implications related to how you would do that. In free space, it's more or less easy to control a region that's about a sixth of a wavelength in dimension, right? So at 100 hertz, that's about half a meter or something. So it's not too difficult to do that with relatively simple hardware. But if you're going to do global control in free space, you have to imagine that there's a sound source and sound is radiating away from this thing. So that if you're going to achieve perfect cancellation in principle, you have to reproduce exactly the entire wave field that this source is generating. And that, in principle, if you look up Huygens' principle, you can, in principle, reproduce a sound field by a combination of layers of monopoles and dipoles radiating, and they can create a sound field that exactly mimics any sound field you wish. But what it means is that you would have to cover the source, as it were, with this layer of sources to try to reproduce the sound field that is the primary concern. So whether that is possible or not is a good question. We've done things with, if you also take a look at multipole expansions of monopoles, quote unquote, you can represent a monopole source with a multipole that's displaced some distance from it, and we have demonstrated that you can achieve significant control over global regions with that in a region that excludes a sphere, including the primary and secondary sources. So you can sort of do these things, but the degree of complexity gets pretty high pretty quickly as you move up in frequency. In enclosures, again, if you put a secondary source very close to a primary source and run it out of phase, what you can do is, in a sense, unload the primary source so that although it's moving, it's looking into an impedance that's effectively zero, so that it does not radiate. And there are various ways of interpreting what's going on in that case. As far as global control goes, there are various schemes involved in doing that. Yesterday, we were in the building acoustics section. We were mentioning that often there are various modes in this space, and each of those modes, in a sense, is a way of conveying energy from one spot to another. So you have, in the presence of the modes, you've got a lot of parallel paths from a source to a receiver location. So very roughly speaking, the low frequency approach is to control the modes in the space, and you need enough sensors and enough actuators so that you've got access to each of the modes from an observation point of view and also from a control point of view. The other thing, active structural acoustic control, I think I was there when this term was born. Chris, Steve, and Phil wanted to come up with a new acronym that they can claim for themselves. So this is ASAC, Active Structural Acoustic Control. And this is an approach that's very similar to what I was talking about with the flow control earlier on, in the sense that in an aircraft application, the sound from the propellers causes vibration of the fuselage of the aircraft, and then that radiates sound into the interior, right? So the first approach described earlier on was to use loudspeakers in the interior of the aircraft to control the sound field that was inside the aircraft. This approach is meant to control the vibration of the fuselage that then radiates the sound. So you're trying to get ahead of the sound field generation by putting shakers and vibration transducers on the body of the aircraft to reduce the sound radiation into the interior. And that's a more or less clever thing to do. The difficulty comes from something that I was talking about in the acoustic sources section. You may remember that the panel, if you've got a big panel, for example, no matter what its vibration is like, if you're at a frequency below the critical frequency, and it doesn't radiate sound, whereas above the critical frequency it does. Okay, so that's a very simple situation. Things with aircraft and built-up structures are more complicated, but nonetheless, some things radiate effectively and some do not. And so the technical challenge with something like active structural acoustic control is to be able to control the bits of the vibration that actually then connect to the sound field in the interior. And that has proven to be a little bit of a challenge, but had the kind of spin-off benefit of developing this field related to so-called acoustic radiation modes, which are orthogonal modes that allow you to identify the vibration that actually results in sound. So anyway, a bit of an editorial comment there, but it's a good thing if you can get between the source and the sound field that you're trying to control. This is a repeat, but just again, the idea that if you've got a flow, if you've got noise that's generated by flow, if you can control the flow, then you can control the sound, right? And that is being pursued in a number of quarters. Same thing in principle. There's a lot of interest in the aircraft world in delaying boundary layer transition, right, to try to reduce drag on aircraft surfaces. And if you could, and there are various active means, suction and involved in doing that. and the same kind of things actually can reduce the noise in the interior that's generated by turbulent boundary layer noise, for example. So we've had this categorization, free space, enclosures, local and global. There's a further distinction, of course, between single channel systems and multiple channel systems. This that boils down sort of simply to this, I think. In a situation like this, you've got basically 1 degree of freedom because you've got a plane wave at low enough frequencies. There's just a single plane wave that travels along the duct, right? So it's a situation that's in principle kind of easy to control. Whereas if we had lots of modes bouncing back and forth across this space, you would need a control channel for each of the modes, a receiver and a secondary source. So in a system where you've really just got 1 degree of freedom, you can get away with single channel systems, but in more general situations, you need multiple inputs and multiple outputs to achieve control, either locally or globally. There's also an issue of feed forward versus feedback. Control, I'm not a controls person, but controls people love feedback control, right? So there's this continuing impulse to use feedback control, but that is not so useful when the signal that you're trying to cancel is continuously changing, right? Because feedback control implies that the error sensor, where you're trying to cancel something, right, you've sensed the signal, then you try to produce a signal that cancels it, right? So if there's physical separation, there's a delay involved in generating the secondary signal that's meant to cancel the first signal. And unless the error sensor and the secondary source are right on top of each other, sooner or later this system ceases to work, right, because of the delays involved. Whereas the idea of feed-forward control is more or less straightforward, that you sense the offending signal before it gets to the point where you want to cancel it, and that gives you enough time to process that signal, feed it to the secondary source, and get it to the point where you want to achieve the cancellation in time, as it were. So generally speaking, in situations where you can sense something about the mechanism that creates the sound that you're wishing to cancel, it's best to use feed-forward systems. In the automotive context, for example, we were talking yesterday about structure-borne noise being important at relatively low frequencies, say below 500 hertz. So a major mechanism involves vibration of the vehicle hub, or the wheel hub, that then connects through the suspension into the interior of the vehicle. And so the feed-forward sensing in that application is to put, say, accelerometers on the hub to estimate what the vibration is that's being experienced there, and then use that and process those signals to generate the signal in the vehicle that then is canceling the sound field that is being produced by that forcing down at the wheel. And that's perhaps a too simple explanation of what's going on, but you have the advantage of the time delay between the forcing at the wheel and the signal transmitting into the vehicle. It gives you a chance to do something about it. So there's that difference between feed-forward control when you've got time to do something and feedback control when you use the error sensor itself as the reference sensor. Also, you have adaptive versus non-adaptive control to where the controller, which is, say, modeling the path between the secondary source and the reference source so that you can cancel the effect of the secondary source on the reference signal. If the environment here is changing, for example, maybe the temperature changes so the speed of sound changes, or if there's a bit of flow here, the flow speed might change. So the system needs to be able to identify itself as time goes on and adjust itself to account for changes as the situation operates. So there's the now classic filtered Dex LMS algorithm that I think Bernie Woodrow at Stanford, I think, was responsible for. And if you ever look up, there are like a zillion citations to his paper on that subject. And then there are controllers with and without feedback path cancellation. Again, this idea that if you generate a signal here, it's going in both directions. And so if you know what the signal is you're generating, you should be able to eliminate it, right, from the signal that you're measuring here, and so generate a secondary signal that is not influenced by the feedback and so on and so forth. And again, this is getting, in English we would say this is getting down into the weeds here. This is maybe more than you need to know, arguably being simpler in structure compared to FIR filters, but sometimes the convergence properties are not so good, so we'll skip over that one, right? And then broadband active noise control versus narrowband active noise control, again, in terms of entire road interaction, very difficult, right? The sort of, in this kind of situation, you know a lot about the signal, right? You know what its frequency is, you know what the harmonic structure is, you know what the phase is, and so it's very easy to generate, well, very easy. It's easy to generate a signal that can cancel these things. Whereas with a purely random signal, you know almost nothing about the signal other than its statistical properties. But in the active noise control context, you need to be able to predict what's happening next, right, to be able to cancel the signal. So, and that is a challenge, right? So that still broadband control, say control of aerodynamic noise, for example, broadband aerodynamic noise is difficult compared to tonal noise. The other thing, almost the last thing here, controllers with versus without online plant identification. This I mentioned the business of the active headrest, right? You are trying to cancel the sound at the passenger's ears here, and in part of the reason, what you need to know are transfer functions between the loudspeakers and the ear location. And that, in a sense, corresponds to the plant in this case. And if the dumb passenger starts moving his or her head, that disrupts the situation, right? But instead of locking the passenger's head in one place, what you can do is continuously run a system identification program to, in effect, experimentally measure the transfer function or estimate the transfer function as it changes by adding small signals to the source, right? So you sort of embed signals that are low enough that they're not obvious to the listener, but nonetheless can be extracted and then used to estimate transfer functions, which can be used to create this virtual sensing situation, because, as I say, you can perhaps put microphones somewhere relatively close to the ears, but inevitably they're not going to be at the ear locations. So there's a lot of work that goes into so-called virtual sensing, where you adjust the signal that's measured at one point to represent the signal that exists at another point, right? And so that's the idea of virtual sensing, that you would try to produce an error signal as if it were actually at the ear location. Good. And so there's a whole bunch of other stuff that people are concerned with: convergence analysis of different adaptive algorithms, ways to reduce computational load, turning multi-input, multi-output controllers into single input, single output under certain circumstances. Using I'm afraid I associate subband with Star Trek, right? Subband communication across the galaxy. But apparently it shows up in active noise control as well, where you're looking at certain frequency bands, downsampling perhaps, to shifting them to other frequencies so that you can do processing faster. Improving convergence properties, finding optimal source and sensor arrangements. And I think maybe the et cetera here should include continued work on making things that are really robust, right? If you, maybe this is not so true these days, but if you buy a refrigerator or something for use at home, I think you would usually expect it to last for maybe 15 years or something without any real attention, right? And I think we're just really sort of getting to the point with active noise control where you might expect it to be able to work in a vehicle for long periods of time. But it's still a little bit fragile because it depends on the health of loudspeakers, which can be degraded over time, and the fact that all of the electronics is working properly without calibration for long periods of time. So I think there's still probably work to be done in that area. But with that, Young Fan says thank you. And if you've got any questions, you can direct them to him. No, I would be happy to answer any questions that I can. Yep.
Broadband aerodynamic noise. Difficult to control.
Yep.
What kind of difficulties, like especially with reference to the aircraft engine exhaust noise, and there are certain active and passive noise control techniques.
Yep.
Like Chevron, microjets.
Mm-hmm.
And they are, I guess, working effectively for reducing the noise.
Well, so I'm sort of more familiar with the aircraft situation, I would have to say. So, with a big commercial jet, as it travels through the air, boundary layer forms over the skin of the aircraft, and vortices rolling up, the boundary layer expanding. And in a sense, if you take a look at the correlation between the velocities in the boundary layer as a function of separation, right, and also the pressure experienced by the fuselage, there's a certain correlation distance, right, which is actually not very big. So that what's happening on the fuselage at this point is not strongly correlated with what's happening on the fuselage at this point. And so you've got the fuselage, in a sense, covered with this array of uncorrelated random sources, right? And many hundreds of them, in a sense, right? And so the sound field in the interior consists of a superposition of all those sources passed through transfer functions involving the fuselage to get into the interior. So if you've got 100 uncorrelated sources contributing to the interior noise, you need, in principle, reference signals that are correlated with each of the individual sources on the exterior of the aircraft to generate canceling signals that then will work on them in the interior. So that really is the issue, I think, trying to extract reference information that allows you to generate reference signals that can cancel whatever is happening inside. The same thing applies to road noise, where at a minimum you have 4 uncorrelated sources having to do with the wheels, as well as the aerodynamic noise of various kinds, and then the power, the engine and stuff. So you've got sort of a dozen things happening at once in a motor vehicle, and that again makes life a little bit difficult. It's great if you've got something like an electric power plant where you know exactly what the rotational speeds are and things like that, and that makes life kind of easy, right? Okay, good. Anyway, thank you.
On the last day session after coffee in the morning. Now I'm going to speak something on case studies on noise control. Okay. And throughout the week we had discussions on these topics. We had Professor Bolton, who was kind enough to deliver many of the lectures in these topics, and we were educated by him. Thank you, Professor Bolton, for your nice lectures. And now what I'm going to do is I'm going to present to you a few case studies which I have done with my team. That is, I owe everything to my students, both past and present, who have helped me doing all this work. And I'm going to give you a brief presentation of what we have done. Well, I must thank my sponsors, or rather our sponsors over the years, and mostly the auto industries in India, the manufacturing industries in India. We have, I would not like to name everybody because of paucity of time, but you can see their logos here on this, who have helped us grow and helped us in kind to develop our lab. As you saw, many of the equipments were donated, were bought from their money, and I would also thank our institute for giving us a nice building for the lab. Okay, and just to briefly name some of my past students, this is Sagar, Vivek, some of them are presently with me, Biswajit, Akash, Debashish, Neha, Shankar, Fatima, Tanmay, Maxim, Prashant, and of course my two dear colleagues, Makur and Kaushik, who are always there with me, helping me with all the activities in and outside the lab as well. And it is because of them we are able to do so many things. And I have some of the students. In fact, this photograph is from a meeting we had a few months back on a course on machinery condition monitoring. So some of my old students came down to this seminar, so we got an opportunity to get their photographs as well. We have a small lab, but it's pretty packed, as we saw, and we have this kind of equipment, a lot of softwares, and then some setups. And then, the issue is maintaining this equipment, and then because we have these things, we are able to do many activities both in and outside the lab, particularly helping the Indian industries in noise and vibration control. And out of these activities is what I'm going to present to you some of the case studies which we have done. I'm going to talk about a few of these case studies in this about hours time, so I may be hurrying some of them. One regarding this environmental noise control, where we have this explosive forming occurring. And let me tell you what this explosive forming occurs. There are two metal plates. One is an aluminum plate, another is a copper plate. Okay, and these are to be bonded together. Okay, and these plates are of the size of about 4 meters by 1 meter and so on. And if you have been to an aluminum refinery, aluminum melting plant, the aluminum ore, aluminum is obtained from the bauxite ore after calcination, cleaning, etc., by an chemical process, okay, or sorry, electrical process, and then the current is given through a copper terminal, and this aluminum needs to be bonded to that, and they make what is called as electrical bus bar connections, and we cannot bolt it together, so they have to be bonded. So in a place somewhere in India, they take these two metal pieces, sheets, thick steel plates, steel, aluminum and copper plates, and lay a layer of explosive. Okay, and then they explode from one area, and this explosion forces moves, and this, because of this explosive forces, these two metals bond. Okay, and that is what is explosive forming. And once this explosion occurs, there's a lot of loud noise, and it happens in a remote area. The reason I'm telling you why is, suddenly in the middle of the day, you'll have a loud explosion. And there were cases where the local communities started to complain because of buildings, mud walls cracking, glasses shattering, stillborn babies occurring because pregnant women are suddenly startled by a big explosion. And this was happening around the year, every day, at least one in the morning and one in the afternoon. So they complained to the local authorities, and then the local authorities, told the regulatory guys that stop this explosive operations which is occurring. So I was called to look into the issues and what kind of noise mitigation measures could be put. So one was, of course, to make a shelter, a concrete bunker, and do the explosive forming inside the bunker. But that is not cost effective. So well, this was anyway being done in a remote location somewhere in eastern India. So what we did, we asked them to have foliage, thick vegetation around this pit where this explosive forming was occurring, and they started to have plantation of long, tall trees. And over the years, the noise, has which is felt in the community has reduced. So what I'm going to say, it's kind of a barrier, but using the natural vegetation to apply and put them together so that this explosive noise is masked to some extent and so on. Now the next one is this plant noise control. We have a steel plant, a small steel plant, where actually from the blast furnace, if you can see a truck out here, and when the castings are done, they come through a conveyor and then they drop onto this, and their castings have just come out of the blast furnace, so they are very hot, and they are metal, so they drop, and they make this impact noise, tung, every. So somebody in the plant, people are irritated by this dropping impact noise. That is one issue where the environmental industrial noise in that plant goes up because of this dropping from an impact. So there was a design where we had an hydraulic mechanism for this bed of the truck to go up so that the drop height reduces, and then the impact noise would reduce, the potential energy would come down, and that noise would just reduce. But in that same plant, what happens, because this blast furnace needs to be fed by blowers giving in clean air into that blast furnace, And if you'll see, there are series of such 5 blowers, and the levels were very, very high. So the way we went around it is, we designed certain enclosures, but putting an enclosure on a blower and a motor creates another problem, is that the bearing, the inside temperature also goes up. So that would affect the bearings of these motors and the blower, and so we have to have certain chillers in the intake and exhaust of these enclosures as well. So this is how the plant noise control could be reduced, particularly in the blower house. Now I will come up to some case studies on few of the engine noise control which we have done at our labs in Kharagpur, implemented them and then seen the noise reduction. So I'll be talking about how this noise source identification was actually done, what kind of measures were put in engine noise control, and the vehicle pass-by noise measurements. In fact, we have a plant very close to us in Jamshedpur where they manufacture engines for many of the commercial trucks in India, and this is in their engine test cell. My student, who is now in Singapore, is doing this engine SIL mapping by our homemade sound intensity probe, and then of course I have shown it here as an SPL. So if you look here, this is one side of this engine on the test cell at 1320 RPM and 55 kilowatt load. You will see in a diesel engine, this fuel pumps, as Professor Bolton was mentioning, they are very noisy, noise producing components, and some measures were done to reduce the noise produced by this fuel injector pumps of the diesel engine. And then of course we also did some treatments to the oil pan and the valve cover, and then finally we implemented it in the engine, and then this engine was put in a truck, and then the truck was driven on our roads in Kharagpur, and then we did pass-by noise measurements. So coming to pass-by noise measurements, there is an ISO 3028 standard, which says when you are right at this location, you ask your driver to go on full throttle, and you're measuring somewhere here about 7.5 meters from the middle of the road on either side. So what is whenever the vehicle moves and then he releases the throttle at this end, whatever the maximum SPL would be your pass-by noise levels. Okay. We did some modifications on this engine, and the oil pan being coated, the valve covers being coated, and if you had shown in the SIL map, the fuel pump was radiating quite a bit of noise. So what we did is we designed a material shield between this mudguard and the wheel arch, and then we had a good amount of noise reduction. These are some values, and this is the truck which we do pass-by noise measurements. It came all the way from Jamshedpur, and then we implemented this new engine. And I don't know if this picture is not that clear, but the shield is already in place. And when we do such trials on this empty road, the villagers nearby on isolated road get excited, okay, and they come and stop by to see the things. So what I will play is, I will play this pass-by noise measurement. So you get a feel as if we are standing in at this location. You're standing at this location. So how you would feel or hear the pass-by noise, the truck going by. Let me see if I can play this rightly. There you go. Oops. Let me see if I can play this here. These guys must have put the audio off or something. So the maximum SPL which you hear is the pass-by noise. Okay. Yeah, that was one project which we did for a couple of the engine manufacturer and the truck guys. And there was another company in somewhere in the middle of central India. And if you'll see this, we are doing we do not have a chamber wherein I can drive in a truck, but on a sunny weekend, we did it on our campus. Of course, I should have been away from this building because it would stop the reflection. But this is close to be a free field condition. Okay. And if you'll see here on the tripods, I have microphones around, and then we are trying to do the free field noise mapping of this truck in stationary condition at different speed locations and so on, speed conditions and so on. And sometimes, it is more important to protect your equipment than yourself. So I put an umbrella actually protecting the microphone power supply than myself. Okay. And some of this equipment need to be powered in the middle of nowhere. If you do not have any power source, better is to use your car battery. I don't know if I have that figure here. Yeah, you can see my old car. I'm drawing off power of the car to drive some of these recorders and stuff like that. And this is those of you who have not been to this museum. This is the old building of IIT Kharagpur. We have a nice museum out there. So we did it on a nice sunny weekend. And then we did this measurement on this truck. And then, of course, we had cranes come and remove the cab. And then we could do very close to the engine noise. We could do the mapping to see what are the predominant noise sources and so on. And I asked my students, why this wet patch here? This is because it's a stationary engine. I need to throw cooling water, okay, so that I cool the engine as well. We had bucket full of water also. So this is the noise map of the vehicle rear in SPL and dBA at idle conditions, half throttle, 3/4 throttle, full throttle, etc. You will see with increase of the throttle, this area, the flywheel clutch housing area, is the most predominant noise producing side in the rear of the truck. And this is on the side view, etc. So these are the areas where this predominantly noise is coming out. Of course, no load. And then once we again remove the cab, we could do a noise mapping on the engine. And here again, the culprits happen to be the diesel pump. And I think I have a list. So in terms of, if you do noise control, you have to do a noise source ranking. And flywheel clutch unit, because it's an open, oil pan, fuel pump, turbocharger, cylinder head, etc. So for every equipment, be it a automobile, be it a refrigerator, be it a railway locomotive, we have to do these exercises. Of course, now we have the most modern instrumentation of acoustical holography, where you can do noise mapping in one go. And we did it the hard way because that's what we had then. Okay. And this is the same location. Once we did some noise control measures put in place, we again do the noise source pass-by noise measurement, and that's on a tripod 7.5 meters far away. Okay. And fortunately in Kharagpur, we are located between two defense establishments. So they have a road which is not used by anybody, and sometimes I sneak in my vehicles for pass-by noise, of course with their permission, and then they allow me to do that. Okay. Now I will come to another topic wherein some of the computer-aided engineering techniques can be used for noise control. Of course, nowadays the mantra in the industry is, we would like to hear the product before even it is manufactured. And that is true even for automobiles. That is true for appliances. This was not the case, maybe 20, 30 years ago, when we used to actually build prototypes and test them at different conditions. And as you all know, prototype building is a costly affair. But now with virtual CAE, computer-aided engineering, and very good softwares for finite element, boundary element, CFD, SCA are available. Computational fluid dynamics, statistical energy analysis are all available, including signal processing. So you could practically, and these softwares are so well tested and well understood, they capture the physics, and you can produce noise, listen to it, and then if you do not like it, you can go back to your design. So that saves you a lot of time, money, and effort. So this is one example wherein I will show you how this noise prediction in the interior of a cabin can be done through CAE techniques. So we have a vehicle cab. Okay, in a truck there is a cabin. This is a work which I did at Ford while I was working with them 25 years ago. So we have the paper on that, which is there in Applied Acoustics. So this cab is actually put on mounts, because an engine could be sitting somewhere else. So basically what happens, forces come to this cab. So the cabs get excited at their mount locations. So whatever be the dynamics, whether you are going on a road, whether the engine is vibrating, I'm getting some inputs at the cabs. So this could be processed and becomes a load data to my structural model of the cab. So once I have a finite element model of the cab, I can do a force frequency response analysis and find out the structural velocities of the cab shell. And then if you think of an air molecule next to it, it is going to have the same amount of vibration. So then I can use a technique of boundary element model method to transfer these structural velocities into the fluid velocities on the boundary, and using boundary element method I can find out the SPL at any location. In this case it happens to be the driver's right ear. And in the boundary element method, if I have in my cabin, say, a headliner, I could give the impedance of that headliner as a boundary condition to one of the at this roof location. I could play around with these impedances. For example, if the absorption is higher, I want to put in higher absorption material, I can play around with this impedance and predict what is the noise at the driver's right ear location. So I'll quickly brush you through the example. So this is the FEM model of the truck cab. When we were working with this model, it had more than 1 million degrees of freedom, and we used to use a Cray supercomputer in those days to solve this finite element model on using Nastran. And then this is the actual model where all the components are there. And this is the boundary element model of the cab, where I've removed the doors just to give you a view of the cab interior. So we can now apply different material properties to this model. For example, your floor could have a certain carpet, your glass could have a certain impedance, the headliner could have a certain impedance, and then you have a boundary element model. And that, by the way, this is the standard procedure nowadays in industry. And this is from the Nastran analysis. You will see once we excite the cab, particularly, and these models are good from 0 to 500 hertz. If you excite the cab, these are the places where the high velocities are there. So this is in turn being responsible for the acoustic response at the driver's right ear location. And we actually, when we excite the cab at the mount locations, all the resonating modes get excited. So it is good from a noise control engineer's point of view by applying materials to reduce the noise at these acoustical modes. This is the acoustical mode of the cab air mass. This happens to be one mode. There are other modes as well. And if you look at this final result of the SPL in the interior of the cab, where we have done a relative comparison with no treatment and two different types of treatment on the roof of the headliner of the cab, by heavy treatment I mean a high absorbing material. So I could bring down the overall noise in the driver's right ear location. So this is a procedure which we published 25 years ago, perhaps. So this is what is the technology today, and everybody for all plants are doing this in and out. Yeah, we talked about auditorium acoustics. I will, in fact, another few things which we do is having the right acoustical material to control the reverberation time, where to put, how much to put, and I will just play, if I can play this, how this impulse looks like, or how it sounds rather. So this is the high impulse, and then we switch it off. So the decay could be found out, that 60 dB drop could be found out. If it's not 60 dB, we can always extrapolate as Professor Bolton was mentioning yesterday. Okay, so this is the decay, and then you can find the RT time for this auditorium, and then you can play around with the materials. But nowadays, of course, there are issues with placement of the loudspeakers, and some of the designs which the modern Inoxes in our theater movie complexes they are doing is they are making the room dead by filling it up with absorbing materials and using electronics to play with the sound field. So that, and there are commercial softwares wherein you can give the sound power locations at different locations where you want to put your drivers and the subwoofers, and the requirement is that every seat location there should be an uniform sound pressure level distribution. How do you do that? So placements of loudspeaker, even the line arrays, the angle of those elements plays a significant role in ensuring that you have an uniform sound pressure level at all the seats. And that's what people are doing, and we help many of the auditoriums and even some open-air theaters wherein we have to place the loudspeakers. And open-air theaters in India, the big challenge is the traffic noise. People honk, and so these issues are there. So we try to put them silent zone, one-way traffic, vegetation. So these are certain measures which we have to do. And in open-air theater, another issue is loudspeakers which are all weather resistant, in terms of exposing them to sun, light, humidity, rain. So the loudspeakers which we use in the interior studios cannot be used. They have to have what is known as this IP65 rating, so that they are robust to environmental conditions. So that's something, and then cost obviously for the IP65 rating equipment goes up. Now I will talk about the software which we have developed. A couple of my students have done that, and we have used that successfully to design silencers for automobiles, for some equipment manufacturer, etc. So I will not go into details of this, which you all know by now. So there is an element library where you can pick your elements and make your mufflers, and the transfer matrices are multiplied, then you could get your transmission loss. Of course, you can also find out the insertion loss provided you know the source impedance correctly. And there are different elements library, and this is the GUI of, I'm sorry, I need to go to full screen. This is the GUI once you put a perforated element and then you can play around with the length, diameter, etc. Open area ratio of the perforate. So it's a very quick trick. This is not a three-dimensional model, and three-dimensional model takes time to model and mesh and do that stuff, but this quickly you can get it some idea as to whether I can reduce the noise, particularly in the plane wave limits of the tube. We have played around for a concentric perforated muffler at varying porosities. We have done playing around with porosities. You will see how this transmission loss would change. This is from one of our SAE paper. Well, putting a Helmholtz resonator along with a perforated resonator, we can kill some of these frequencies because of this Helmholtz resonator being put. Okay. We have a recent paper wherein we have also estimated the tailpipe sound and done a sound quality analysis to find out which is the critical muffler parameter which influences the jury. And then I had a couple of students, not couple of, in fact, a lot of students who came down to our lab and evaluated, and this full paper is there on evaluating and finding out the critical parameters of these mufflers. Now I'll come to another case study where we'll talk about how the noise control of a refrigerator is done. And by now perhaps you all know, for noise control to be implemented on any machinery, noise source identification, path characterization, property evaluation, and then matching with the right kind of materials developed. Is it structure borne? Is it airborne? If it is airborne, what kind of materials, where to put? And so all this, I will go through some of the results which you have done for this refrigerator. And this we did for an MNC, and where we had an overall reduction of about 5 decibel, and this technology which we implemented. I would not discuss this here on this forum, but we have shared it with the MNC in North America. So this is the details of the refrigerator. It's a 3-door refrigerator. Those of you who visited our lab, maybe you saw a couple of these lying around. So the idea was to remove the radiated noise of the domestic refrigerator because of the fact that in small dwellings, where particularly we have practically no kitchen. We have just a hall where in one corner you have an open kitchen where there is a refrigerator in small dwellings. So in the middle of the night, this refrigerator compressor kicks in, and then after a few hours it shuts. So this creates a sleep annoyance. So the manufacturers would like to quieten their refrigerator, was their mandate which they gave us. And we tried some technology and we were able to control it. But of course, before we found out the exact source, we did some sorts of instrumentation, and these are all instruments which we have there in our laboratory. And this is out of our paper where we presented at one of the ICSVs. So we tried with the compressor, because there are two components here. There is in a refrigerator which have motion. One is the compressor, and another the evaporator fan. So of course, we tried all the combinations of on, off, and blah blah, and then we found out the SPL. And this is the sound pressure level as a function of frequencies, with fan on, compressor on, fan, both of them on, and so on. And then of course we did a sound intensity level mapping for the entire refrigerator, so that to find out which is the most noise producing element, is it which component. So before we did the SIL, we were not sure whether it is mostly the evaporator fan or is it the compressor at the bottom of the refrigerator. So SIL very easily gave us that information. So if you look at the sound intensity level measurements of the refrigerator at all 5 surfaces, obviously we could not go to the bottom of the refrigerator. And if you see here, the compressor sits the bottom 48 dBA, the most noise producing element in this refrigerator, followed by the evaporator fan, which is on the top. So any noise control measures which has to be implemented to reduce the noise control has to be first tried at the compressor. Okay. Of course, compressor sits on the mounts. So a lot of the structural energy from the compressor is propagated through those mounts into the shell of the refrigerator. Okay. So we have to see whether we could play around with these mounts to ensure that the structural energy from the compressor does not go too much into the refrigerator shell. Of course, we also did the sound power level measurements using nothing but multiplying the sound intensity with the area. And for the structure-borne noise measurement, what we did, we removed the compressor, and at the mount location we excited it mechanically, and then we found the transfer function between the structural location at the mounts and the SPL in the interior of the refrigerator, and we plotted that. So if you'll see here, this is the exciter, and of course the signals and all that, and we have the excuse me, we have the microphone inside, because there's a 3-compartment the refrigerator. One, we have the freezer compartment excuse me, then we have the refrigerator and the pedestal compartment. So you can see here in this figure, the compressor is removed. We could not totally remove because of the tubings, but you could displace it. And then I gave in a structural input wherein we could know the forces going into the shell of the refrigerator and measure the response in the interior of the refrigerator. And if you'll see here, this white shiny marks, they are the marks where for the laser vibrometer. We wanted to later on study, we wanted to also see the shell of the compressor was radiating any sound, so we wanted to measure the vibrations using a laser vibrometer. And also we did a numerical analysis using a boundary element software to use this as a source and find out what is the noise radiated because of the compressor shell. If anything could be done to the material of the shell, to the mounting of the shell, so that the noise could be reduced. Because the manufacturer says, this compressor is not manufactured by them. They outsource it from some other country at a very low price. So the quality of the compressor could be influencing the product of your refrigerator, the quality of your refrigerator. And as said, if NVH engineers are not cared for, people would buy the cheapest compressor and don't worry about the damping present or the mounting conditions in the compressor. And this was an issue here. And we could not change the supplier of the compressor because they were under a contract, but of course we could play around with the mount stiffnesses. And I'll tell you how this mount stiffnesses for compressors, or for that matter for anything, could be measured. Stiffness is nothing but K is equal to F by X. So we always measure the static stiffness, but then if you want to measure the dynamic stiffness, where it is a function of frequency, we have to also excite the system at different frequencies and simultaneously measure the response at those frequencies. So for this, I'll come to that stiffness measurements in a bit. And then regarding this airborne noise measurement, what we did is to see the effectiveness of the door seals. Similar to your automobiles, when we have wind noise coming in, many of them come through the windshield and the door seals. So door seals play a big role in reducing the noise from outside to inside. So similarly in a refrigerator, we wanted to see what is the noise in the interior of the refrigerator that is coming out because of the seals. The effectiveness of the seals could be measured. And we did it in an inverse way. We, instead of putting the source inside, we put the source outside and we measured the noise inside and saw the difference. This is this omni source, sound source, and then these door seals are very important. Omni source driving for the airborne excitation, and then you can see the path for the structure borne and the airborne. And as you see, the structure borne in this case happens to be predominant again at low frequencies, and airborne is high at higher frequencies. This is typical for some of these machines of that nature. So structure borne is predominant from 0 to 100 hertz. So it is this mounts which are the naughty guys in this case of the refrigerator. Okay. So this is how we measure the dynamic stiffness of mounts. Okay. So we have this mount which we press against a hard wall. I give the force, and this is an impedance head driving it. So you can simultaneously measure force and acceleration. So from the acceleration we can get the displacement. So you can see this axial stiffness of the mounts. It is not a constant. And this is very important because when you do a dynamic CAE model, sometimes if you know the displacement, if I know the stiffness, I can know what is the force coming, and F is equal to Kx. So the value of K can be measured and put in your numerical model by this method. Okay. And this we did an FEM and BM model to predict the noise. So door seal effectiveness measurements. So this is the microphones which are put, and these seals are very, very important. Okay, and if you look at the modern cars, some of these cars have a single layer seal, some have 3-layer seal, and if you have traveled in the Rajdhani coaches, you would have seen how important these window seals and the door seals are, and compared to the normal sleeper coaches. Okay. So you know how effective this seal is, because we talked about flanking path. You have a nice thick shell, and the shell is good transmission loss, but you have very poor seals at the doors, and that is true in many of the applications which I have seen, and we will see how the seals could be improved to reduce the noise, be it an automobile, be it in locomotive, be it an appliance like a refrigerator and so on. Of course, this refrigerator, we did the seals. In some frequencies, they are not working as well. But we have an overall about 15 dB noise reduction because of the seals. Of course, my students were excited, so you did some numerical modeling of the compressor shell and refrigerator shell. And of course, they measured it because this would become the boundary conditions to the boundary element software and numerical results of the modeling of the compressor. Okay, then numerical modeling. And this is the result. You can see these are more experimental observations, and this is because of the compressor. This is from numerically. So this is just to demonstrate that whatever you spend a lot of money on the experiments, on doing the actual things, but if you are able to numerically predict it, it's good enough. So now you can play around with the material properties and try to see whether the noise could be reduced. And this is the state of the art today. Okay, model building takes some time, but then if you have some good models developed, you can play around and reduce the noise. Of course, we had a reduction of 32 dB, 5 dB, and it came down somewhere from 35 to 36. We had some variations, and of course, associated with this is also the sound quality. You reduce the noise because this product is going inside your so-called open area in your dwelling. So you would not like to get irritated by the noise. So there is a requirement that of course, there's the overall noise reduction. There is a requirement that we look into the roughness aspects of the refrigerator without treatment and with treatment, and then things came down and which were appreciated. But any noise control measures which you put in a refrigerator, because the primary function of a refrigerator is to keep your food cool. Okay, whatever NVH treatment we do, if we screw up their thermal functioning, nobody would like to buy that refrigerator. So the end client was very careful that we do not disturb their thermal performance. So we always also did a thermal mapping, because NVH engineers are the last guys to be called into. Okay, and then we did a temperature logging of this refrigerator in the lab for many hours to see if the thermal performance deteriorated or no. It was fine and it was acceptable. This is through the thermal imaging camera, you can see, and then if you can see here, a lot of thermocouples been put in the refrigerator, compressor cabinets, etc., so that we are monitoring the temperature and logging it for many hours after we have done the treatment in this refrigerator to reduce the noise. Okay. Now I will come to another project which we are currently working on. I will discuss some of these issues here in terms of noise source identification, and then rest we will discuss sometimes later on in the breaks perhaps, because many of this data is not yet published, so I would not like to share all the data in a public lecture like this. But again, whether it is a railway locomotive or a Dornier aircraft, they have noise problems in HAL also. So, or whether it's an automobile truck of any company, everybody has noise problems. Okay? And whether it is plant, etc. It's good that they have noise problems, so they keep us busy. Okay, and my students learn and so on. So we have to do an interior noise measurement, exterior noise measurement, noise source location identification, and then same procedure which we followed for the refrigerator is also to be followed for the locomotive, and we have done that. I will just share with you that we had the railways were kind enough to give me a big locomotive to play with for about 10 days at our workshop in Kharagpur. So it was a thrill that we had this 10 days this locomotive all to ourselves, and the loco drivers could do whatever we wanted them to do, at what speed, what engine conditions they were driving it, and me and my students were measuring it, and then we had characterized this sources, and we have found out the places where we are going to implement certain measures, and which I will be discussing with my clients next week, and what we want to do. And this is in the cabin. We have put a microphone, and then we got to drive this locomotive, because I was not driving it, but I was there in the loco with the instrumentation, and it was real fun going from Kharagpur to about 60 kilometers down and coming back on an open track. And it's nice that they give you priority, okay, on the tracks. Research engine on the way, that's what they say on the walkie-talkie. So we had real fun driving it on a rainy morning, okay, and then collecting the data. This is the part of the instrumentation. I don't know if those of you have visited my lab, you would have seen many of these yellow suitcases on the shelf. Sometimes the suitcases are costlier than the accelerometers. You know? Okay, and then my favorite tool is my DAT recorder and the conditioning amplifiers for the accelerometers and the microphones. So obviously we cannot do any in situ analysis. So we record the data, bring it back to the lab, try to understand the path and the levels and so on, and then we implement measures. I will just only share with you one data, rest all data I cannot share in this forum. This is the loco speed, this is the time, because incidentally I was surprised myself that today the locomotive are very similar to they have a similar thing compared to the flight data recorder or the cockpit voice data recorder. Today, every parameter of the locomotive is logged into a computer as soon as you start the engine. Whether the driver was overspeeding, what was the engine speed, what was the load, what was the speed, everything is logged into it. So the drivers of Indian Railway were very thrilled when they came to know that an IIT professor is going to help them out, reduce the noise levels on their locomotive. By the way, I would not like to tell the levels, but they are in very pitiable conditions, driving for 8 hours, no loo in the cab, and going at such high noise levels is tough, okay, from a personal point of view. But then one driver was excited, so he oversped, and you can see the speed. Even from Kharagpur to another station which we are going, we went and then stopped there, and then if you see the time stamping here, then we again came back. So I have the vibration data, noise data, both for a running engine, stationary engines at different speed conditions. We have found out what the noise sources are, what is the path, and hopefully, down the years you will see a quiet noise locomotive for the Indian Railways. Okay, so let us see how that project goes ahead. So this is just to briefly give you some of the activities which you do in terms of some case studies, and I could go for hours on case studies, but just to give you an idea. So anywhere you have to do noise control, please understand the basics, measure correctly, number one, know the limits of your instrumentation, and then identify the source, the path, know the technology available, apply them, evaluate them, and that's it. It's that simple. It's no rocket science, let me tell you. Noise control is not rocket science. Okay, it's very easy provided you follow these procedures. Well, this would be my last lecture in GIAN, but Professor Bolton will be there in the afternoon. But I would like to thank individually my students who have helped us put in some of the materials. Devashis, whom you would have been seen busy with the camera. Sneha was taking a lecture on sound quality, and she is working on a lot of stuff on holography, CFD, and acoustics, and so on. Akash is doing on noise source inverse problems. Of course, I'll come to Professor Bolton at the end. Professor Biswajit is working on signal processing, Maxim on underwater acoustics. Fatima was our student, but she came in to help us on the GIAN program. She's working on natural materials. And my special thanks to Professor Stuart Bolton from the Herrick Labs of Purdue, who came down to India for the first time, and he has been here, as you will see, for all the 20 hours, very religiously, following us, give us excellent inputs to what is the state of the art in noise control. More important than that is the physics behind acoustics, and I thank you, sir, for teaching us acoustics. And well, the thanks goes to the GIAN team who all are here, the participants, okay, and I would not name everybody, but then this is there so you all can see. I would like to thank our continuing education office, our CET, the guys in the back who are monitoring us, recording us, putting it on the web, and again my thanks to my colleagues Ashok and Kaushik, on all the students from outside, people from the industry, academia who have come, and I hope you all have enjoyed this course. And many things we'll be putting on our website, iitnoise.com, and then you can contact me if you require any information. Some of the slides of Professor Bolton in due course, we are going to put it in that site so you all can download and see it. And thank you all. I hope you all had a good time at Kharagpur.